Okay, so this is section 9.4. We did the comparison of series. Comparison of series. Okay, so we did this one in class, a direct comparison test. The biggest conclusion you draw from that theorem is this one right here. It's at the bottom of the paper. If the larger series converges, then the smaller series must also converge, right? If the larger series converges. So this is this theorem, this direct comparison test. If the larger one converges, then the smaller one also converges. If the smaller one diverges, then the larger series must also diverge. So that is the biggest conclusion you need to make. All right. Now, the better test is actually the limit comparison test. The limit comparison test is one of the more useful tests for divergence or convergence, because this actually answers both of them. Like, it will tell you if it converges or if it diverges. Like, remember, the nth term test for divergence only tests for divergence. Okay, the integral test is pretty good, but it's a whole lot of work. This is actually less work. All right. So what are you going to do with this? So let's look at the theorem test. So if you have a sequence, right? So this is sequence. So this sequence is part of this series. So A sub n is part of this series, and B sub n is part of this series. If you take the limit of those two, and you get an answer, and it's finite and positive, and keeping in mind that A sub n and B sub n also have to be positive, then they both behave the same way. So if you get a numerical answer, it doesn't have to be 0, right? It could be any number, but it has to be positive, and it has to be a number. It can't be infinity. Okay. So if that limit exists and it's positive, then they behave the same way. So looking at this one, 1 over 3n squared minus 4n plus 5. So what will be a good thing to compare it to? Well, a good thing to compare it to will be 1 over n squared, right? We know about 1 over n squared. From the p series test, we know that this will converge. So take the limit of that. So you're going to do limit as n goes to infinity. Right? I'm just taking the limit. And it doesn't matter which one's on top. 3n squared. So I'm putting the sequence, or the a sub n, of my given series over the one I know about. Okay? We know that 1 over n squared converges by the p series test, and p equals 2. And then we take this limit. When you take this limit, so let's do some algebra. This ends up becoming n squared over 3n squared minus 4n plus 5. Right? So basically, if you divide by a fraction, you take the reciprocal of the fraction. When you take the reciprocal of this, it ends up being n squared on top. What's the limit of this? The limit of this is 1/3. Right? Therefore, by the limit comparison test, since 1 over n squared that converges, then this one converges. Okay? So determine the converges, it converges. By limit comparison test, since 1 over n squared converges by p series test with p equals 2, which is greater than 1, and by the limit with a limit of 1/3, 1 over 3n squared minus 4n plus 5 also converges. Now I know that's probably pretty bad grammar. I'm sorry. All right. What about this one? So what would you compare this one to? So I would compare that one to, say, square root of n. Right? 1 over square root of n. So let's take that limit. N goes to infinity. 1 over square root of 3n minus 2 over 1 over square root of n. Compare that. That's going to be limit as n goes to infinity of square root of n over square root of 3n minus 2. And that will be 1 over square root of 3, which is greater than 0 and finite. So I know 1 over square root of n diverges. So I know this one diverges. So divergent. So by the limit comparison test, it diverges. Okay, I'm running out of space, so I'm not doing that. All right, look at C. So what would be a good comparison here? So you might think n to the fifth, but there's an n squared up here. Okay, so what I would compare it to is what's the difference between those two, right? The difference is n to the third. So I would compare this to 1 over n to the third, right? And we know 1 over n to the third converges by the p-series test, right? It's p equals 3, so this converges. So I'm going to take this limit as n goes to infinity of n squared minus 10 over 4n to the fifth plus n to the third over 1 over n to the third. All right, that's going to be limit n goes to infinity. So that's going to be flipping up and multiplying. So that would be n to the fifth minus 10n to the third over 4n to the fifth plus n to the third. Right, so the n to the third end up multiplying the numerator of that. Okay, so we know the limit of that. That's equal to 1/4. So converges. So the series n squared minus 10 over 4n to the fifth plus n to the third converges by the limit comparison test. Okay, and what about this one? So you got square root of n and n squared. So if you use the same rules as last time, by simply subtracting the exponents, this will give me an exponent of 1.5, right? So what do we know about? So basically, I'm looking at n to the 1.5, right? N to the 1.5, or maybe 1 over n to the 3/2, whichever you're more comfortable with. Does that converge or diverge? Well, p is equal to 3/2. It's bigger than 1, so this converges. So we're going to do multiply by n to the 3/2, or I'm sorry, take the limit. So limit as n goes to infinity. I want to write n to the half over n squared plus 1 over 1 over n to the 3/2. Okay, so that multiplied by that, that's going to give me a limit as n goes to infinity of n squared over n squared plus 1, right? So whenever you have this fraction, you're going to multiply n to the 3/2 times n to the half. So you add the exponents, 1/2 plus 3/2 gives me 2. And that limit is 1. It is positive and finite, so they behave the same. So it converges by the limit comparison test. Okay. Ooh, doggy. What do I do with that one? All right. So you might, well, what do I do with that one? So you got like 2n, and you got this 4n cubed. What do I compare to? So you might think, well, do I compare that to n squared? Do I compare that to 2 to the n? Well, I got to tell you, 2 to the n in the numerator. Oh, I was thinking I wouldn't even do the limit comparison test to this. And I would use an nth term test for divergence. But looking at that limit, that might be painful. So limit comparison test. So what would I compare this to? Well, I'm thinking I'm going to compare it to 2 to the n. If I compare this to 2 to the n. Now this diverges. By geometric series, the ratio is greater than 1. So this diverges. So let's do this. So limit as n goes to infinity, n 2 to the n over 4n cubed plus 1 over 2 to the n. And if I were to clean that up, that's going to be limit as n goes to infinity. And that actually cancels, and you get n over 4n cubed plus 1. Right? And this limit is 0. Uh-oh. That is not a positive number. So that was a bad choice. That was a bad choice because that's not a positive number. That's 0. 0 doesn't count. You can't. If the limit goes to 0, that's not a good answer. So what's a better choice? How about 2n over n squared? Let's do 2n over n squared. Well, what do we know about 2n over n squared? What do we know about 2n over n squared? All right, so looking at this, you're going to say by the nth term test for divergence, this one diverges. Right? This one diverges by nth term test for divergence. If you let n go to infinity, 2 to the n is going to overpower n squared. That's not going to 0. That's going to infinity. So this diverges. So this is a trickier one because I have to prove what I'm going to show is divergent. Right? I have to prove this one. Like this is not a common series to look at. So I'm talking about this thing, right? I'm looking at this thing. This is not a common series. This is not a series we have a rule for. So I have to prove that it diverges. This diverges by the nth term test for divergence. Now let's compare it. So this was a bad choice. I'm just crossing that out because we don't want 0. If we get 0, that was a bad choice, right? Because remember, it has to be positive, where L is finite and positive. Well, 0 is not positive, so that was not a good choice. So let's try it again. So limit as n goes to infinity of n2 to the n over 4n cubed plus 1 over 2 to the n over n squared. All right? So when we deal with that, so it's limit as n goes to infinity of n2 to the n over 4n cubed plus 1. I'm going to do a little more showing my work here. So that's going to be times n squared over 2 to the n. So the 2 to the n is going to cancel. So I'm going to have n cubed over 4n cubed plus 1. Okay, that limit is 1/4. Okay, that limit is 1/4. So now we can say, okay, it's a positive number. I've shown that this diverges by the nth term test for divergence. So that means the original series also diverges by the limit comparison test. So we say this diverges. Okay, so that's that page.